So good morning all the participants and good morning Supriya Madam. So I welcome you all for our fourth day of faculty development program on robotics, the machine power for industrial automation. So today the session 1 is going to be handled by Dr. P. Supriya, Associate Professor, Amrita Vishwavidyapeetham University, Coimbatore. The topic is multiple robot path planning using various techniques. So before starting the session, I would like to read the profile of Dr. Supriya Ma'am in this forum. Dr. Supriya P. joined Amrita School of Engineering in the year 1996. She did her BE from Coimbatore Institute of Technology and MS in Electronics and Control from Birla Institute of Technology, Pilani. She has around 46 publications in international conferences and journals. She has 16 years of teaching experience in postgraduate programs and more than 25 years in undergraduate programs. Dr. Supriya was the co-investigator for internally funded project in 2006 for remote load control using wireless network. She was also a co-investigator for the DST Vinnova Smart Grid project with KTH. Sweden Energy Management using embedded system for 2011-2014. She had coordinated an IEEE conference on embedded system in 2014, ICES 2014. She is reviewer for several Elsevier and IEEE journals like IEEE Access, Journal of Robotic and Automation, International Journal of Power and Energy, and Electric Power Components. Her research interests includes embedded system-based design for smart grid, power system harmonics and signal processing application to smart grid, and software solution to robotics and automotive applications. Now I hand over the session to Dr. Supriya ma'am. Thank you, ma'am.
Thank you. Good morning, all participants. Am I audible? Yes?
Yes, madam, you are audible.
Sorry, I think I was muted. So here, my idea is to keep the multi-robotic path planning towards the end. I would be starting with path planning. So the flow is going to be something like this. I start with why path planning is essential, then why we need multi-robotics, then we move on to some commonly used robotic path planning techniques, and then we go on to some simple examples of robotic.
Sorry for the interruption, ma'am.
Yeah, I think it is.
Are you sharing your screen, ma'am?
No, I'm just not sharing. I will share in a few minutes from now. I'll just have an introduction, then I will share my screen.
Okay, ma'am. Okay, ma'am.
So it goes with various techniques, and then I would like to present some of the. Basically, they are all PG projects, so you will see professionalism only to that level. Some examples or some demonstrations of the work done by those students, because most of them have been converted to papers, and you will see the references also include the papers that are done by those students. So as I move on, if you have any queries, do let me know. Because as I'm sharing the screen, I will not be able to know. Maybe you need to unmute and tell me. Otherwise, once I go into the other screen, most probably I'll be concentrating on that side and I'll not be aware that you are putting a question. And I plan my session like this. First 45 minutes, I will be going on with one of the conventional algorithms. It may go on to around 50 minutes. Then last 5 to 10 minutes we will have for a discussion. Then we will go on with the second algorithm. Similar way, we will stop at 50 minutes and go on for a discussion. Same thing would follow for the remaining sessions also. Is my screen visible? Now I have shared the screen.
Yes, ma'am, it is visible.
Yeah. So my basic idea is to start with the various path planning methods, as I mentioned, and 2 words about the institute where I have spent almost, as you have heard from the introduction, 25 years at this institute. So Amrita School of Engineering, Coimbatore, is the headquarters for the deemed university, Amrita Vishwa Vidyapeetham. Most of you might have heard about this university. The College of Engineering started in the year 1994, and within 10 years of its start, we grew into a deemed university. We started off the EEE department in 1994 itself, and at present we have 4 PG programs in the EEE department, and we have also started one more UG program, namely the Electrical and Computer Engineering program. In addition, the MTech programs were started in subsequent years. We started off our first MTech program in Power Electronics in the year 2004, and that was on Power Electronics. Recently, it has been renamed as Power Electronics and Drives. The Embedded Systems was started in the year 2008. The MTech Renewable was started in the year 2013, and Industrial Intelligence Systems was started in 2018. So I move on to my presentation. I'll be going on in this particular fashion, as I had mentioned. I'll be discussing about, in this particular session, I'll be discussing about A star. Then I'll be moving on to other algorithms as we go on. And finally, as I mentioned, CNN is just an introduction perhaps. And finally, we'll end up with what is going to be the multi-robotic systems. And maybe some of the few applications will also be dealt with. And finally, we will end up with the references which I have used for my presentation. Most of us are aware of these points because we've been hearing these for the past 3 days, as I mentioned in my introduction. So robots have 3 major parts: the mechanical part, the electronics part, and the software part. So can we relate the robots to the human life? Because finally, what are we trying to do? This itself is a good example of what is going to be the essence from robot. We would like to get the assistance from the robot for our various activities, maybe the medical field, maybe the agricultural field, whichever field you name, now robots are taking over. So what is it if we say in terms of real life? We would say that human life goes on aging. In the young age, we are behind monetary gains, trying to save a lot, especially the Indian mentality is for saving a lot of money for the future. So there we have an analogy with the fabrication of a robot, which is the basics of a mechanical system, because only if your robot is robust, we can go ahead, and it should have very good movement, and also it should have only limited joints. You might have already heard from other speakers that more number of joints results in complexity and control issues. So this is similar to our young age. But what happens during our middle age? During our middle age, we would like to try spending this money, move out, go to various places, visit places, etc. And it is here that robot path planning comes in, because when we want to reach a destination, what do we think? We have a holiday coming up. Maybe the nearest holidays now is the Christmas. Let us think, what can we do for Christmas holidays? We have maybe 5 days, 10 days, depending upon your institution. And if we have these holidays, what can we do is our thought. And the thought comes that some of us may go to nearby places, some of us may be religious, we would like to go to some temples. We may have various thoughts, but a major thing lies there which controls our thoughts. It is money. That is, economically, will it be feasible? Will it be possible for us to manage the trip? And so many things come into our thought. This is exactly what is going to be the software which we are going to build into the robot to make it move. It should be quite efficient, or it should be quite fast enough, and it should be correct in the sense that it should take the robot to its destination. It should not waver around and just be wobbling, things like that. So electronics and software are like the middle age of the human being, wherein we may have a similar situation when we are thinking of planning a vacation. The first issue is, shall we go to India, or in places in India, or shall we go abroad? So you have a choice, and as I mentioned, based on our economic feasibility, we decide to go for a foreign trip. Then the next thing is, what type of flight should I book? So we have so many choices. Similar to that, we are also going to have so many softwares which could perform the same path planning or reaching the destination. Our problem is what? That is what we are going to discuss, and we will initially be discussing the various algorithms, and then perhaps go on to see how we can measure them, what could be the performance indices. And finally, during our final old age, we are going to reap the benefits of what we have worked during our young age and middle age. I think nowadays, more than money, it is health that matters, especially post-COVID. Most of you will agree with me that most of us are bothered of our health. And this health is also equivalent in young age, middle age, and old age. Young age, you are very brisk, you are very energetic, you are very active in all fields, in all domains, be it your personal life, be it your academic life, professional life, whichever you call it, you are very, very active. But what happens as you go on to the middle age? Your mentality changes. So that's the same that we have discussed. And old age is going to be, I said, reaping the benefits of young and middle age. So it's like a robot is going to be successful in moving around and do some things. I think most of us are very happy to see such an example, right? Especially if it's an application like it starts doing some agricultural help or cleaning. Now you could see that for cleaning, vacuum cleaning, so many things, you are getting robo as a very good assistive product, or even in places it is replacing human beings. So as we move on, what is going to be the major task for the robot? The major task for the robot, if I say, as I mentioned, is that it should move in the right direction. Like we said, human beings have planned for a vacation, we should make it true, and we should also see various issues like the climate of the place is important. If you have children, they may get sick, then are you having health issues? You yourself may be having, your spouse may be having health issues. So many things are required. So similar to that, here, only one task we are discussing at the present, that is movement in the right direction. And as a result, we are going to discuss about such a task which is going to be in robotic language called as path planning. And this path planning is very essential for the robot to move. And major thing is that it should avoid obstacles. When it avoids obstacles and moves to the destination, we feel that there is a success in the path planning algorithm. You will see that this path planning is a concept not only specific to robotics, it could be applicable to other devices also, like self-driving cars employ algorithms for path planning. Maybe they use more of image processing based algorithms, because They are going to take the photograph of the road and things like that. And UAVs also employ the path planning because they have to move around, and you should give them a specific region where they should move and where they should monitor the region. So for that also, path planning becomes essential. So though this has been specific mentioned for robotics, you are aware that it can be generalized and applied to various areas. When we come to the path planning, the basic idea is a software. And as has been mentioned, the software that we could think could be represented in terms of algorithms. These algorithms could be conventional, it could be machine learning based, or it could be decision based. So based on this, we are going to discuss two conventional algorithms, namely one of them is called as A star and the second one is called as Digistra. So based on machine learning algorithms, we are going to discuss reinforcement learning. Basically, it is going to be a temporal difference learning. We could also extend it to an advanced form of reinforcement learning, namely the SARSAB algorithm. And finally, we could also extend our problem to the machine learning based on either RNN, that is recurrent neural networks, or conventional neural networks. So several regions are still lying unexplored. We could explore those regions and try to understand what could be the basic idea of such a path planning. So what is exactly path planning? How are we going to deal this in our discussions? Are we going to discuss it in terms of fields, that is a normal method that is used in robotics, or are we going to use it as grids, which is another method? There are several methods, of which generally the grid-based is supposed to be superior because of its efficiency in making the spaces to squares of equal size, and the robot could be placed at the center, and we could almost make the size of the grid such that it is equivalent to it is matching, or it is such that the robot lies in the center of the grid. So if you go in for the basic terms that are involved in path planning, the first term is going to be the source. That means we say that the robot starts from a starting point, or this is the source point. Several terms are used, and then we go on to see that has the robot reached its destination, which is a common language, or in robotic terms, it could be called as the target or goal of the robot. And the next one is going to be, there will be so many obstacles which the robot should avoid, and it should reach the destination. These obstacles could be of various types. It could be static, which are known type of obstacles, or dynamic, which are unknown type of obstacles. Especially when we talk about self-driving cars, you see that one of the major things that comes is going to be the dynamic obstacles. Not only self-driving cars, other real-time applications, most of them have dynamic obstacles. So once we have developed our algorithm for static obstacles, we should try and implement it for dynamic obstacles. And the last term that we are going to discuss is going to be the optimal path. There can be several paths to reach from the source to the target. So if you just see, here I have considered a grid. This grid I have named it as, if you see this, it is a 4x4 grid. 1, 2, 3, 4, 4 locations. That means there are 4 rows and there are 4 columns. Is it right? So since we have 4 rows and 4 columns, we are going to have this as a 4x4 grid. That is how it is technically referred to. And if you see the starting point of the robot, we will see that this is going to be the starting point, and the starting point is generally represented as 0, 0. The target is going to be mentioned here as a star point, and our major aim would be the optimal path. The best path is, since there are obstacles here and here, the least path is the optimal path, and it is going to be from the source to the target. This is what most of our algorithms need to attempt That is, make the robot reach from the starting point to the ending point, or what you call the destination or the target. What are these grids and how are we going to name them? When we talk about the grids, I mentioned that here we are going to have it as, if you see this is the zeroth row. You could see this is the zeroth row. This is the zeroth row. Then we have the first row, which is here. Then this is going to be the second row. So this is going to be the second row. And this one is your last row. Actually, we call it as 1, 2, 3, 4. But in robotic terminology, we generally start the numbering from 0. So it's going to be the final one, which is going to be 3. So just like we had 4 rows, we are going to also have 4 columns. Namely, this is going to be our 0th column. So you could see this particular cell where the robot generally stands is going to be represented as 0, 0. And this is actually the starting point for the robot. So next we have the next column, which is going to be 1. So this is going to be 1, and any position in this column will have on its right element 1. That's not been mentioned. So if you take this, we could write this as 2, 1. Similarly, if you consider this one, this is the second column represented as 2. Actually, it is the third column. So here you could see we have represented this. This is the first row and this is the second column. So since this is the first row and second column, we would be representing this as 1, 2. This is going to be 1, 2, representing the first row here and the second column. And moving on to our target, that is, the target is in 3, if you see. You know that this is 3, and as a result, we would be representing this as a column named 3, and as a result, this location is going to be 3, 3. So this is what we see as our robotic path planning and the naming of various cells. As I proceed, can I just ask a query to the audience? May I know what is the position of this particular obstacle? Yeah, anybody could answer? May I know what could be the position of this particular obstacle? It would be 1, 0. Yes? Okay. Similarly, what would be the position of this particular obstacle? Yes, it could be 0, 1. So as we move on, we would see that we can also have other paths, like this is the second path. The first path is in blue. So the second path is, it moves like this, it goes like this, it goes like this, and finally it reaches. This also is a path in the sense that it also reaches the target, and a major concept that is there in path planning is obstacle avoidance, and obstacles are avoided in this particular case too also. We can also see one more case, which is the third case, and here you would see that it is starting from the starting point, it is avoiding the obstacles, and still it is also reaching the target. So what is of significance to us is a term which we have called now as optimal path, which means we would like the robot to reach the destination with minimum distance. This distance is generally calculated as the Euclidean distance, and we could see several other types of distances also employed in various algorithms. So once this particular grid structure is clear, we can easily understand how the algorithms could be planned. And here we have taken an example of a grid which is going to be 4 by 4. So this particular grid, we would like to call it as 4 by 4. We could have other types of grid, like we could have a 5 by 5 grid, 6 by 6, 8 by 8, anything is fine. And in irregular surfaces, we could extend it to regions which could be approximated to the nearest next grid, so that the space covered by the robot is not ignored. So once this particular idea is clear to us, we can easily understand that we require either a single robot to reach the target or a multiple robot. Why do we require a multiple robot? First, let us go on to see the various issues with the single robot. Whenever we have simple tasks like just reaching a target, we could easily plan for a single robot. It could have various joints, it could have a very complex architecture, whatever it could be, it is very easy to implement a simple task with a single robot. Next, we have a requirement where we may require a spatial distribution. And under such a spatial distribution, we would generally see that if we want, for example, in missile launch, as has been given an example for multi-robo, we could see that we have an example where two keys need to be activated simultaneously, and then only the missile launch should happen. So if we need two keys to be activated, we would like to use multi-robos, and as a result, we would like to go in for such multiple robots which would activate the keys which are separated by some spatial distance. So for such spatial distance applications, we would like to go in for multiple robots. There are several examples where multiple robots are gaining over single robots. One of the examples is a complex task, and in locations where spatial distributions is required. Of course, from the reliability point of view also, we could have a simple path planning technique with multiple robots where in case there is a failure of a first robo, the second robo can take over, or if first and second robo fail, then also the third robo can take over, and so on, depending upon the location and the size of the area where the robo is being covered. So this makes us clear that we would like to move on from a single robo perhaps to a multiple robo in situations where we require complex tasks. For simple tasks, we have discussed that single robo is fine, but when we want the complex tasks, as we have mentioned for a missile launch, which requires some sort of a synchronization, under such a case, we would like to go in for multiple robots. So that is one of the examples where multiple robo could be used, or in examples where I mentioned that reliability is of utmost significance, wherein you need the task to be completed at the earliest time may not be a first rate importance. It may be just that the task gets completed. So in case one of the robots fails, you can have the second robo to take over. But for simple applications like for removal of weed, for sowing the field, etc., that is term which we use as smart agriculture, perhaps it may be sufficient to go off with a single robo, and perhaps we could use a robotic arm-based robo which could do the smart agriculture part. Or another application could be a parcel delivery, where mostly a single robo could do in case our destination is quite simple. On the other hand, if the destination turns out to be a little complex, maybe we may have to go in for multiple robots. So this is giving you a general comparison of can we go for a single robo or a multiple robo, that is selection of a robo for a specific application. And again, moving on, you generally see that The cost is going to be lower than making several robots, and then implementing would be easier than having a complicated mechanism embedded into a single robot and that robot resulting in a failure. Other advantages of the multi-robotic systems include system reliability, flexibility, scalability, versatility, and so on. And as I mentioned, the system performance is likely to be better when we use multi-robotic systems, because if we want our job to be done, it may be possible that one of the robots get damaged or it fails due to mechanical problem, software problem, electronic problem, the three problems that we have, the three issues that we have discussed for the making of a robot. And whatever it happens, the second robot can take over, assuming that the second robot is in a full state where it could do its job in a successful manner. And moreover, communication between the robot is another significant part that may help us to bring in the concept of multiple robotic systems. So when we talk about robotic types, maybe you have discussed this issue also, there could be homogeneous type of robots or heterogeneous types of robots. Whatever may be the types of robots, that is, the multi-robot systems may have three robots which are of same make, same fabrication, or they may be of three different makes. You're aware that several commercial robots are available, which you could be using it for lab implementation purposes, especially Next Robotics is a startup of IIT Mumbai, which could implement, which could provide you also with such robots. They have the Spark Robotics, the Firebird type of robotics, iRobo, so on and so forth, which could be used and combined in a combination. When they are combined as three different types, you may be calling it as a heterogeneous type of robo. But if it is the same robo, for example, it is R1, R2, R3 are all of the same make, we say that it is a homogeneous type of robo. So when we implement multi-robo systems, this also is likely to bring in small amount of difficulty unless we are using the same type of communication module. That is one of the major issues, because when we use a multiple robo system, repeatedly I've been mentioning that communication is of greater significance for its implementation. So here I have presented a small classification starting from the various conventional methods like A-star, Dijkstra, remodel A-star. These are the conventional type of algorithms which most of us may be aware, and if at all we are not aware, they are quite simple for us to implement also. Artificial intelligence based. I think yesterday you have had a session, maybe it was covered, fuzzy, genetic based and machine learning based, where you could have reinforcement learning, and I have discussed the simpler one, which is the temporal difference learning, and slightly better performance-based algorithm called as the SARSA. We could also have highly ended machine learning-based algorithm like CNN. So this gives us an idea that various types of path planning algorithms are available, and as I mentioned, maybe you have discussed this in your session yesterday. So let us now start with the simplest algorithm, namely the A-star, and let us go on to see how this A-star works. What is this A-star? So if we go in for A-star, we know that whenever you talk about robotics for path planning, the first thing that comes to anybody's mind is that it is one of the most popular techniques available for path planning. And as a result, we could see that the shortest path could be found very efficiently using A-star, and several significant applications are also built on A-star. So in case you are going to start implementation, many of you are quite senior people who might have worked in various fields, who might have worked in robotics, might have worked in all these algorithms. I'm talking about people who are new to this robotics, where you could easily start with A-star because it's a very simple algorithm, easy for us to understand, and also it gives the results in a quite efficient manner. And you would see that it is one of the algorithms that employs the best first search type of optimization, and as a result, it gives better results than the next type of algorithm that we may discuss, which is called as Dijkstra. So what is the structure of A star looking like? If we go into the structure of A star, what we generally see is that it has a tree of paths which starts at the start node, and we will see this with an example. We will be extending these paths one at a time through the edges, and we will continue till we reach the end. The major thing that we require in A star is its function, which is called as the minimizing function, wherein it is given by f of n is equal to g of n plus h of n. So if you see this, you would see that g of n is going to represent, I would call it the distance path. And h of n is a heuristic function, as the term says, and it would represent how significant the node is, or you could change the value of h of n depending upon your need, right? So h of n is going to be a function which will give you a value, which is assigned a value based on how you want your path to be planned, and gfn is going to be the distance from the starting node to the next node, to the next node, so on and so forth. Let us try to understand the concept of these two. That is, let us try to understand what is going to be g of n and what is going to be h of n by considering an example where we may have around 10 nodes starting from A to J, and let us see how we can travel from A to J. Various options are available. What is the solution that is going to be given by A star? So the major point lies in the function of h of n. So A star is based on the mathematical expression given by f of n is going to be equal to g of n plus h of n. So let us go on to the graph which I was mentioning. Here, if you see, we have got several nodes. The first node is A, then we have B, C, D, E, F, G, H is lying outside, I, and G. So here we have 10 nodes as I mentioned, and you would see several values are available. You would see here there are some values like 6, 3, 5, 5, etc., which may be in black or brown color, and you would see at the nodes some values are also available, like you would see these values available. You have 10 at node A, at B you have 8, at node C you have 5, so on and so forth. For various nodes, you have various values assigned. So what are we trying to do with each of these values? So if we consider what we are going to do, that is what is going to be the basic idea of the algorithm. That is, as you can see, the number on the edges gives us the distance between the nodes, and the number on the nodes gives you the heuristic value. So this is where I mentioned this is going to be your heuristic value, or it is going to be the priority with which you are going to take a particular node. So can I say that if I have a choice from A to B to F, the priority I have given for B is more than F based on the heuristic value that I have given. But of course, it will also be based on the distance, because here you will see the distance is more. So naturally, the value is also going to be more. This is what is meant by the heuristic value, a value assigned to the node, which is going to be based on priority, on based on a value that you would like it to either ignore, or it could be a best first search is what we have said. Since it is going to be a best first search, we would like to avoid a particular node by either increasing or decreasing its heuristic value. And as you can see, this represents the distance. It could be in centimeters or in meters, whatever it might be. So this is going to be the graph which we are going to take up for understanding the A-star algorithm. So as we move on, let us try to find out the path as we have mentioned, starting from A to J. We have several paths. Let us try one of them. It could go this way. Another one, it could go this way. Here again you have two paths. Maybe I will choose this one. Maybe some of you will choose this one. There are so many possibilities that are likely to happen, right? And why only that? We could also have several other possibilities, like we could start this way, we could move on, and even this is a possibility. So as I mentioned, so many possibilities are there. How are we going to find out? That is exactly what this particular algorithm does. It gives us the optimal path based on the function that we have discussed. So let us start, as we have said, our starting point or our source in robotic language is A, our target is going to be J, or our destination is going to be J. So when we start with node A, please note we have two possibilities. One is we can go to node B, another one is we can go to node F. Which node are we going to choose? This is going to be evaluated by us by applying the equation of A star given by f of n is going to be equal to g of n plus h of n. Let us see how this expression is going to be applied. So to apply this expression, we will start with what is going to be the values of g of n and h of n for these two nodes and see whichever is lower, A will move on to that particular node. So let us start with, as I mentioned, calculating the function of f of b, f of node B, and the function of node F. These are the two possibilities where node A can move from its starting position. So how are we going to choose this value? We have this as f of n. So this first value is going to be f of b. So g of n, you know, is 6, and h of n is going to be 8. So you will see that this is going to be 6 plus 8, which is going to be 14. Let us see that you have got that same value for f of b, that is, it is 6 from here, the distance from A to B, g of n, and h of n is the value, cost function that we have assigned, or the heuristic value that we have assigned to the node, represented in green. So here we have h of n, that is the same here, so we have got 14. What happens to the function of f? When we go to the function of f, it was looking like we may get b as the solution, but here the distance is very less, so it is only 3, and the heuristic value is 6, so it is 3 plus 6, which is going to be 9. So anyway, we have chosen our destination, the next node, which is going to be naturally node f, because we know that node f is going to be lesser than node b, and as a result, the path is going to be from A to F. So we have reached from A to F. We need to still go in to reach J, and this is as per the A star algorithm. Other algorithms may have other solutions and other scenarios. If you consider the different values of B, it may go in for the B part, right? So is it all right? Can I proceed? So we move on to the next node, that is going to be, how are we going to start from the position F? We have reached from A to F. From F, you could see we have two possibilities, G and H. Which one are we going to select? So if we are going to select, we need to naturally calculate the function of the A star given by f of n is going to be equal to g of n plus h of n. So as a result, we will be having this function as the distance is going to be, if you take for f of g, it is going to be 3 plus 1. To take and reach from A to G, it takes 3 plus 1, and heuristic value is the value represented at the node, it is 5, so it is going to be 9. And if we go for the other value, it is going to be 3 plus 7, and the heuristic value at H is 3. Since it is 3, we would say that we are having the value as 7 plus 3, which is our total distance, plus the heuristic value, which is 3. So our total value is 30 for f of h and 9 for f of g. Which value would be chosen? Naturally, we are aware that it is going to be f of g, and we could see here node g is the chosen node, so we have reached node g. From there is only one path. Still, we need to calculate that function, and then we need to, now here we need to adjust the function such that we are going to have the destination as j. So what do we do? We have reached from A to F and then to G, and now we are yet to take the path. Naturally, the only path that we have is I, so we will be following the path of I. From A to F to G. That is what we have achieved. So from here, and again, naturally this is going to be, and we should be getting this as our final result. Let us see how that is going to be got. Is it right? Can we try? So as we move on, we could see that we need to calculate it for f of I, and for f of I, it is going to be, the distance is going to be 3 plus 1 plus 1, sorry, 3 plus 1 plus 3, so that's going to make it 7, and the distance given here, which is going to be 8. It's the only possibility, so naturally it reaches node I. From node I, it has to take a path to J. That is going to be the final path. So to make it to the final path, we are just going to apply this particular expression. Please note, it's now going to have several possibilities. That is, it could go to node E, it could go to node H, and it could go to node J. Right? We are not restricting the algorithm by saying that it should not move backward. So as a result, it can also move backward. So all options are available to it, and we need to see which is going to be our least option. So we start with evaluating the function for node E, which is going to be 3 plus 1 plus 3 plus 5, and the value at node 3, which is going to be 15. So the value of the function f of E is going to be 15. We need to see whether the other two choices are lower, so that it is going to choose those two possible values. Next we go from node H. It is going to be 3 plus 1 plus 3 plus 2. So it is going to be 9, and a 3 value which is subtended by H is available here. So that gives you 12. And finally, what is the functional value for J? Please note, there is no heuristic value attached to node J. So by all possibilities, even if the distance is going to be larger, because there is no weight or what you call the cost associated with the node, J is going to be most probably the chosen solution. That was the guess perhaps, and that is going to be the solution. So 3 plus 1 plus 3 plus 3, that's going to make it 10. So as a result, we know the least part is going to be the J, and we have reached the destination, which is going to be node J. Okay. So we start off by moving into path A, to path F, to path G, to path I, and finally it reaches path J. So this is what we had planned, and finally this is solution that we have got if we have considered these specific heuristic values. So this is going to be from here, goes to here, then goes to this path, and then goes to this is what we have got as our path. And we call this particular path as optimal. Maybe you could get different solutions based on the values that you assign to these nodes. That is, now perhaps an idea might have come that A star is going to be basically based on the heuristic value that is associated with each node. So generally, how are we going to write the algorithm? We have understood the example. Let us just try to conclude the A step by just defining the algorithm and discussing the algorithm. And then we will go up with a sample of how to implement this algorithm onto a robot. So here we have basically two lists that are available. One is going to be called as an open list, and the other one is going to be called as the closed list. And if you see the closed list, it is going to have the list of all unvisited nodes, and this is going to be having all the nodes that are going to be evaluated by the heuristic function. So once these two are going to be available, we are going to proceed with these two nodes, and naturally towards our end we should have the final path which is going to be available in the list enclosed by closed. So let us go ahead. So as we go ahead, we see that, as I mentioned, we will be defining the list of open, and the list of open at present when you start has only the source or the starting node, which we call it as S. There are no other nodes available in this particular node, and in step 2, if we have no nodes, that means we have started with, in this particular example, we have started with node A. If you have no other nodes available, it means that we have either failed or the algorithm is not working. Actually, the path is having more nodes. It should return some other value, and thereby it should go on to the next node. So next, what we are going to do is the smallest value of Fn is going to be removed from the open list, and we will be leaving it to the closed list. So as we have seen, the present case, we have evaluated that we had node A. From node A, we were trying to move on to node F. So you would see that node F is going to be a function which was evaluated over node B, and as a result, it is going to be taken from the open list to the closed list. And if we have reached the destination, we could stop. Otherwise, we should proceed with node N. So that means we should proceed with node F. So when we have the node F, what we try to do is, we try to go in to reach the destination path from node F, as you could see here. Here we have called it as node S, which is actually the node A, which moves from F to G, and thereby it keeps on moving. So if F is going to be the destination, we could easily stop. Otherwise, we could keep on applying the function f of n. This is what the step 6 says. From f, you need to apply the evaluation function named as f of n is equal to g of n plus h of n to reach the next node. And some nodes are not there in either open or closed, then such nodes we can add it to the list of open. Example of that in this particular case would be node D. And once we have reached the destination, we can keep on repeating it, and if the destination changes or if the source point changes also, we can suitably modify the algorithm. Is it fine? So can I proceed with my hardware implementation and how we go about doing the A stuff? Yes. Yeah. Okay. So next what we are going to discuss is Is the screen visible? Hello, is the screen visible?
Yes, ma'am. Yes, ma'am. It is visible, ma'am.
So what we are going to consider is going to be how are we going to implement the software algorithm that we have developed now. Various options are available, and it depends if you're going to go in for only software simulation. Perhaps, as you are aware, you could choose MATLAB. If you're going to choose an implementation, you could perhaps move into Python, which is supported by mini controllers, or any specific software which is supported by a suitable controller in which you are going to put this particular code so that the robot starts moving. So the two things that I have shown here are MATLAB, which is going to be for the simulation environment, and Python. I have mentioned it for the software environment. Actually, an embedded controller has been used, so actually the actual function has been done in C. So here you could see some examples of the results which we have got in MATLAB for the A-star algorithm, and to keep it simple, I have taken it as the first four set of values, that is the first four set of values represents, that is this one, this one, this one, and this one is going to be the basic values could represent whether you're going to go in with different source points or whether you're going to have the same source point. Please check the first one. So if you check the first one, it starts from 0, 0. This also starts from 0, 0. This starts from 1, 0. And if you see this one, this is going to start from 1, 1. So different values may be available where you could have your algorithm to start from different source points. Here again you could see different source points. This is again another source point where you have 3, 0. This is again another source point which could be 1, 0. Similarly here it could be 0, 0. Here of course these two are again 0, 0. So you could see a mix of various number of same starting point and various number of obstacles. That is the first four of them. That means this one, this one, this one, and this one actually just indicate the results of no obstacle, one obstacle, two obstacle, and three obstacles with the same source point. And these four actually show a difference when the source point is varied. Still, the algorithm is rigid and it is able to continue following the path. So as I mentioned, this is the code with the MATLAB, and how do we go about with the hardware implementation? Because any fascination in robo is achieved only if we see the robo move, and that's exactly what we need to attempt to. And we need to start off by implementing it on a robotic platform. The robotic platform that throughout most of my implementations I have shown is going to make use of the iRobo, which is, as I mentioned, a vacuum cleaning robo. This is available online. Various versions are available, and the advantage of this is that if you see at this point, there is a serial port. Various ports are also available, and you can interface the controller easily. And it has got rigid wheels. 3 wheels are available. 2 wheels at these two ends, and the front wheel with which the robo can move quite efficiently and in a robust fashion. Similarly, this is technically called as iCreate Robo. Similarly, you could see that various embedded platforms could be used for implementing this algorithm. Now, the most popular is Raspberry Pi, but the application has been using the ARM Mbed LPC 1768. That's why I said the actual implementation has been carried out not on Python, it has been carried out on C, and you could see that ARM boards are Embed boards are also readily available, so we could use such boards for implementation. And in order to interface the robo, we need ultrasonic sensors which needs to be connected to find out the distance or the movement of the robo, sense it and pass it on to the controller to implement the algorithm. So though there are several ultrasonic sensors, I have just mentioned the ultrasonic sensor which has been used for the application that we have. And you could have Bluetooth module, transceiver module, etc. for several communication examples. So here I have a simple snapshot of a simple robot which is hardwired, and you could see that here we have interfaced the ultrasonic sensor. Here there is a robo. We have the power bank because iRobo easily drains when we use it even for a short time. The internal battery is not able to do all the verifications or testing that we may require. As a result, it is preferable to have a power bank which would support the power both for the embed controller as well as for the iRobo, which could be charged and placed inside the iRobo. And we have an LCD which would display the distance that has been covered. So to move on to the video, it is going to just mention what I have shown. Two cases. That is the first case where the robo is moving to the destination with obstacles introduced in its path. The example makes use of the floor of our extension of the embedded systems lab at the university, which is mainly designed for checking this robotic applications, where the ends are used for hardware testing. And the second one is when the source changes, or actually it's an example of a destination change, still the robot is going to reach its destination. Actually, the work was fuzzy-based implementation where it was initially started off by A-star. So you could see that this is a square grid. It is actually 160 meter by 160 meter. Each grid size, we have chosen it as 40 centimeter. The reason for us to choose 40 centimeter is considering the size of the iRobo. The start point is 0, 0. We have a destination at 0, 160, which represents our 30, and another destination represented by 160, 160. You could see as she's introducing the obstacles, it is avoiding and moving on. It is going to the destination 160, 160. that was one example, and we move on to the second example where, as I mentioned, it is almost a similar thing wherein we are going to run it for a different destination. So you could see that it starts from 0, 0 and tries to move towards 0, 160, which is ideally 0, 0 for us, and 3, 0, which we have considered for the simulation example. So you could see that the robo is continuously through some jitter, so it is just trying to rotate. So as we end the first technique and first part of my presentation, we have gone through why path planning is significant in robotic systems. Then we have discussed various possible algorithms, though we have not gone in deep, and we have considered basically the simplest A star with example and the algorithm which could be implemented using the list functions, and how we could implement it, port it to a robo and see the result. Any queries? So maybe I'll move on to the next session, that is register. Yes, any queries from anybody?
Participants, you can post your question in the chat box, or else you can unmute your mic and you can ask queries to me.
I think I have got one example that the voice is quite low. I am already using headphones. I don't know whether it's only for one participant or for others also. Is it for all of you? Voice is not audible? Hello?
No, ma'am. Actually, your voice is audible, ma'am. After that, your voice is audible, ma'am. Okay, thank you, ma'am, for your excellent presentation. Dear participants, ma'am is going to continue her presentation in session 2. So session 2 will start by 11:45 a.m. Okay. So kindly fill up the feedback form for the session 1 and then join the session 2 by 11:45 a.m.
Sir,
Okay,
I
thank
can
you.
proceed with half an hour more also if you want. Because
Sorry, ma'am.
I can proceed with half an hour more also. Actually, I stopped this because it's going to be the next topic.
Okay, ma'am. Ma'am, actually, at what time we can start the session 2, ma'am?
It's up to you, sir. Like, if you want me to start, uh, since your actual break is, as per the schedule, it is at 11:30, I thought I
Yes,
can
okay.
finish one more algorithm by 11:30. I
Okay.
just finished, I put them, I gave them a chance for discussion so that if there is anything that I could correct, I would do it. And then I can proceed with my small session it is till perhaps 11:30. Can I proceed, sir, or you want me to go for a break? Because it's too
No
early, I
problem.
think.
Yes, no problem. We can proceed, ma'am. Actually, the
Okay, sir.
session will end up by 11:30 only, ma'am. Now time
Yeah,
is
so yeah, I can proceed. I can proceed.
sure, sure, sure.
Thank you very much. So we have seen A star. A star, as we have discussed, is a very popular algorithm. No less is the next conventional algorithm, namely Dijkstra. If some of you are working on self-driving cars or on UAV, most of you must have used A star or Dijkstra. As a result, which one would you choose over a choice given A star and Dijkstra? Preferably, we would start with Dijkstra. The reason being, I could have started with Dijkstra, but it is too simple of an algorithm to explain. So I thought that we may start with A star. So here, it is almost the same like A star, but there is no heuristic function. And another difference is that the shortest path is considered, as you can see in the slide. Based on the shortest path, we will be moving on to each location or each destination, and sometimes it ends up in a solution which may not be too optimal. This is one of the drawbacks that we have seen in Dijkstra, and you would see that as it moves from each source to the next one, it would keep on trying to identify, as I have mentioned, the shortest path. So basically, the Dijkstra is based on greedy best first search algorithm, unlike the A star, which is based on best first search algorithm. So here, if you are going to see the basic idea of how we are going to move on with Dijkstra, it is almost similar to what happens in A star. We have few nodes marked as visited nodes. If a node moves from A to B, the visited node will be node B. If it has not moved to the next location, all other nodes would be remaining as unvisited. That means if the path is remaining, or if the robo is remaining at the starting point itself, we would call it as the unvisited, all other nodes as unvisited. So we keep on continuing with the process till all the nodes are considered, and finally we try to calculate the shortest path. So let us proceed to what could be the path. By now most of us are aware that from the source node to the destination node, you would want to reach the destination within the shortest time, and that shortest time, how it is possible, is what we need to work. So the algorithm basically starts as we would mark all the nodes as unvisited, and then we would start by beginning with a starting node which would be marked with a distance of 0, and all other nodes would be marked with infinity. So we will be calling this starting node as the current node. How is this going to be done? And for this current node, we will try to analyze all the nodes which are not visited and try to calculate the distance by considering their distance from the current node with the weight of the node and keeping on adding them to get the final solution. So we will be comparing the present distance which we have got to the distance which we have assigned to the node, and we will make this particular distance as the new distance of the neighboring node. We will consider all the unvisited neighbors and mark all the nodes as visited, which means if we have a graph which is having nodes like what we had seen in the previous example from A to G, in the A star, only few nodes were visited which were of the shortest time, but in Registra we will have all the nodes to be visited starting from the starting node till the last node. So what it appears as an analogy would be, we may start from our starting point. Our starting point would be a point where we are going to have, as we have mentioned, the zero value, and from there on we would start moving to various places. And while moving to various places, it is essential that in Registra all the nodes are visited. And in case we have the destination node to be reached, then if it is visited, we would say that the algorithm has stopped. And each node is going to be chosen as the visited or unvisited based on its distance, and we will be repeating the process till we reach the destination. So let us go on with an example. Perhaps the example will talk a lot more than what has been mentioned as the algorithm. You could see here the number of nodes has been reduced. We have made it into a 5-node structure. What are the nodes? As you could see, this is node A, this is node B, this is node C, this is node D, and this is node E. One major difference that you would see with A star is going to be that in A star you have some heuristic values associated with the nodes. That means we were trying to give some values which we were representing here as maybe some 5, some other value which we may be calling it as 10, etc. But here that value is not given. So what we have is, we have only the distances across the nodes. So if you see this particular diagram, we have between node A and node C, we have a distance of 1. Between node B and node C, we have a distance of 7. Between node A and node B, we have a distance of 3. Between B and D, we have a node of distance of 5. Between D and E, we have a node of 7. And between node B and E, we have a value of 1. So this is the distance which is tended by each of the nodes. So we will be considering C as our reference node and trying to calculate the various distances. So let us start by such an example that we have attempted at, and the first value is going to be, we will mark that the distance for node C is 0, and as a result we will mark this distance as 0, and we will also keep a red dot to show that this particular node is having the minimum distance, or this is the node which is under reference. All of the nodes, just like in the previous case, will have a weight of infinity. Initially we have not given a weight, later it will be given a random weight. Previously we were assigning the weight, here all the weights are uniform for all the nodes. You could see that infinity is the value given to all the nodes. It is the same for all the nodes. Once we have given this value, next the reason for giving infinity is that we are not clear about what is actual distance of node C with the specified nodes. That is why randomly we are starting with node value as infinity. Unlike the previous case, I repeat, where we could see we had specified heuristic values like A could be given 5, B could be given 10, E could be given 15, and so on. So once this has started, what would be our next step? Our next step would be, we will be checking the various neighbors of node C, like we will start with node B, we will check another neighbor called as node A, we will also check another neighbor called node D. So starting from the starting node, which is node C, we will go to various other nodes like B, A, and D, which are the three possible nodes which are possible as the neighbors of node C. Since we are going to consider node C as the starting node and our neighbors are B, A, and D, let us see what happens to node B. So to node B, what we will be doing is the minimum distance will be assigned between C and B. It is 7. So we will cross off infinity and we will write the value of 7 that has been given here. So now the node B's value is going to be 7. Next, we will be considering the minimum distance of 0, which is for node C, to 7, and the distance of node C to B is now considered as 7. So this is how we have reached the first distance. Similarly, we can see how we could arrive at the other nodes, namely node A and node B. So let us make an attempt of how we will be trying to achieve other nodes, namely node A and node B. So I repeat it, we have a set of nodes. We have considered the node with minimum distance as the reference and we have referred it as the dot. We have also given a distance value of 0 and we can consider the neighbors of node C, which are going to be B, A, and D. And out of our neighbors, we have started at present in this particular slide, we are discussing node B. So the minimum distance of node B is going to be 7. So we are crossing off infinity, which we had assigned as the weights for all nodes, irrespective of their distance. Now we are changing the infinity to 7 because the value is obtained as 0 plus 7, which is going to be 7. So naturally, if this value is lesser than the previous value, we'll be retaining that value since we are going to have the lower value is what is going to be assigned. So since 7 is the lower value, we have taken up 7 for node B. What do we need to do next? What we need to do next is we need to consider the next node, which is going to be node B. Node B, as usual, if you see, it is going to be this node has got a value of 0 and here it has got a distance of 2. So we will be crossing over infinity and writing the value of 2. The same thing could be done for node A. We will be crossing the distance of infinity and writing the value of 1. Because by principle, now we know that the distance is calculated at 0 plus 2, so it's not infinity. So let us now be realistic and write the value of 2. So we have two visited nodes, B and D. The next slide is going to be where we are going to choose that naturally 2 is less than infinity, so we would like to choose 2 as the lower value. And next slide is going to be how we are going to choose node A. As you can see, node A would be the minimum distance would be, we have this distance as 0, so 0 plus 1, so that is going to be 1, and infinity is crossed, and we write the value of 1 for node A. So this is how we have had nodes being written. Once this is being done, what do we do next? So we have got that the values of nodes A, B, and D, which are neighboring nodes of node C, have all been replaced with infinity, which means C has visited all its neighbors. So we are going to give a check mark for C. Our ultimate solution is going to be, let us wait to get all the entire graph to have this check mark. Once this is done, it is as though we have all the nodes visited. So how is this going to be attained? So once node C is attained, let us now go on to detect or select a new current node. It could be either node A or it could be node D. So preferably we will go to node A as it is having the minimum distance. So we have put a red dot on node A and we have left the distance as 1 itself, and we are going to consider the next two possible values of node A, which are going to be node B and node C. Naturally, node C cannot have a lower distance and it is also a visited node, so there is no need to discuss about node C. What we need to discuss is from node A to node B. So we need to replace this infinity and now check the distance. It is 3 plus 1. So infinity has been already replaced by 4 by 7, and this 7 is again going to be replaced by the new distance, which is going to be the distance of node A, which is not 0, it is 1 plus 3, so it's going to be 4. So we are going to score off 7 and now write it as 4. So the minimum distance from A to node B is now 4, and we have given that value as the value at node B. So this is what happens. That means we have replaced the distance with minimum distance. So node A does not have any other visited neighbor. Perhaps you could suggest what could be the next step. Since node A has no other visited neighbor, naturally we should put a check mark for it. So that is going to be our next step. We will be putting A as the check mark because it has only one unvisited neighbor, that was B. Now we have visited it and B is having a value of 4. Now we need to choose which could be the current node. It could be either node B or node D. You know that the current node is chosen based on whether we are going to have a minimum distance given by that particular node. So between B and D, we would go for node D. So we would go for node B, and as a result, node B is given a red mark. Now we need to see what could be the distance of node D to node B. It is 5. Please note here that 5 is greater than 4. So we leave the previous value, which is 4. And here from D to E, it is infinity here. So now node E will be marked with 9 instead of infinity. That is 2 is the value of node D plus 7 is the value of the distance between node D to node E. As a result, our final value will be node 9, value of 9. So as I mentioned, first case is we are checking for node B. When we consider for node B, we are getting the value as 5 plus 2. So it is going to be 7. 7 is actually greater than 4. We don't want to replace 4 and go back to a higher value. So we leave it as 4 itself. So the next node that we would like to discuss is going to be that now node B is going to be the node B has got both its visited value, as I have mentioned. For node E, the value is 9. We have replaced infinity with 9. And now between 4 and 9, the lower distance is node B. So now node B is going to be the current node. So since it is going to be the current node, its value is going to be to node E is going to be 4 plus 1, 5. 5 is lesser than 9, so we can replace this with 5. So now node B has also visited all its neighbors, we can also check it. And since E has now the reference node, we would see that it has got all the nodes as visited, so we can easily mark the check for it also. So what has happened has been from node C, we had got two options. We could go to node A, we could go to another option was to go to node B, and the third option was to go to node D. Because all the values were infinity, we saw that we have chosen their distances with the current distance, so we have replaced them with 2. Here we have replaced it with 7, and here we had replaced it with 1. And since all the nodes were visited, we had checked it. Then we had started off with node A. We had checked the distance of node A to node B. It was 1 plus 3, so we had marked it as 4, which was replacing the earlier value of 7. So that is node A is also visited because it had only one node, which was node B. Similarly, the same thing is true for node E also. Then we had considered node B as the reference. We had a choice between node B and node D. We took node D as the reference because it was a lower distance. Since it was a lower distance, we could move from 2 plus 5, that is 7. So we retained it as 4 itself, and here it was going to be 2 plus 7, it was 9. We replaced the distance as 9. So since node D visited both its neighbors, we had ticked that also. Then we had the shift between node D and current node choice between node B and node E. Node B had a value of 4 and node E had a value of 9, so B was chosen. So the distance from B to E was 5. Earlier distance was 9, so we gave that as the new value, and now the value chosen is 5. So all the nodes are visited. Can you suggest this path that can come out of the solution? Yes. From node C to node E? Yes. Let us try to find out the path. So we need to find out what could be the path from C to E. So one path could be to find out the shortest path, though there are so many possibilities. Let us try to see what are the possibilities. The first possibility is from C to B to E. Yes. And you could see that that is giving a distance of 8. Yeah. Any other possibilities? Yes, participants. Any other possibilities we can have? We can have another possibility, C to D to E, that is going to be 9. Any other possibility? Yes. 2 possibilities we have completed. Any other possibility, or only these 2 possible values? Actually, what we will see is there is one more value possible from C to D to B to E, that is also 8. So it is here that you will see that the algorithm results in 2 shortest paths, CBE and CDBE. Maybe you will choose which one is now a dilemma, because if you're going to base it on distance, you are getting 2 separate solutions. And most of our algorithms are such that they should result in a unique solution. So what are we to do? Naturally, we will take the next option, that the number of nodes covered, let us consider them as minimum. So if we are going to consider the number of nodes covered as minimum, we could consider this as CBE over CDBE, because there may be a lag when it reaches each node. You could see that in the video. As we were seeing the robo move, it doesn't move so smoothly. It has a certain lag as it moves. So that lag is what we would have at each node or at each position. So perhaps in addition to the distance, we should also keep that minimum nodes visited are also another criteria, which is actually not an original part of Digistrum. So as a result, what can we do, or what are we arriving at? We are arriving at a major problem, that is, we are not going to have only one solution, we are having more than one. This is one of the major problems of Digistrum. So, as we go on to the various simulation results which have been carried out in MATLAB, as we have seen in the previous discussion, we would see that the starting point as usual is 0, 0, the final point is 3, 3, and you are having various options. You are having no obstacle condition in the first case. In the second case, 1 obstacle, and in the next case, you have 2 obstacles. This case, you have 3 obstacles, and in the last case, you have 4 obstacles. And by now, most of you are also aware that on the x-axis, we will be having the distance covered in the x region. We will be having the distance covered in the x region, which we are calling it as grid. And this is exactly what I was mentioning. You could have a grid size of 160 by 160 centimeter, where each square could be 40 by 40. That was the value that we had chosen in our previous example. The reason being, considering the size of the iRobo, we had to choose that grid size as 40 centimeter. So here we could have an example where it is moving from the starting point to the final point with various number of obstacles. Moving on to the hardware implementation, here you could see that we have placed the grid and we have used a different type of implementation, wherein the controller remains the same. We have used the same embed controller. We have used a similar structure. Only difference that we have done is we have made the grid more intense and we have brought in the obstacles which are still lighter, just to have a check over the register. So as we come to the summary of our presentation, we see that we have tried to understand the second algorithm, which is Dijkstra. This particular algorithm is very specific in the sense that it is only considering the distance. So the major difference with this and A star is that in A star, if you recall, we were writing it as f of n is going to be equal to g of n plus h of n. And you would remember that this particular h of n was responsible for the heuristic. That heuristic value is not available in this particular case. This particular heuristic value is not available in the Dijkstra. Because this is not available, you would see one more drawback, that it is likely to create more than one solution, as we had seen in our example. So we had gone in for the basic algorithm of Dijkstra, where we were trying to consider all unvisited nodes over visited nodes and see the software implementation results in MATLAB and how we have implemented the Dijkstra in hardware. So now the major difference that we have understood with Dijkstra and A star is that it is having an additional heuristic function which is available in A star. And I had mentioned one more algorithm in my presentation in conventional algorithms, namely remodel. No need to be scared. I will not be explaining that algorithm. In that, we will be having one more parameter which is going to be considering the priority or significance of each node, so as to help us to plan the destination node reaching in a faster time. So this is going to be our second algorithm, which is only going to be considering the distance from the node to the next node and thereby trying to reach the destination with all nodes considered. It is not going to leave all the any node. As a result, it is a time-consuming algorithm. So in applications where time is a limiting factor for us to get results, Dijkstra may not be a good solution. So I end my first session now. The floor is open to questions. Any queries that you have? Yeah. I think Venkatesh has asked a question. Yeah, please, Venkatesh. Hello.
Sir, Professor Venkatesh, sir, do you have any doubt? Since you raise your hand in between the session, if you have any doubt, you can ask me, sir. Venkatesh, sir.
These are some of the two algorithms that we have discussed. We may go on to slightly more different algorithms in the next session, wherein we will be also introducing the concept of multi-robots and seeing how the multi-robot are going to be implemented in real time. A simple example is what I'm trying to present in this particular session.
Thank you, ma'am. Thank you for your excellent presentation. So, dear participants, you can join the session 2 by 11:45. Ma'am is going to continue her presentation in the session 2. Okay, thank you very much. Thank you, ma'am.
Thank you. So what time are we meeting next?
Madam,
There seem to be no queries. Yeah.
Madam, 11:45, ma'am.
Okay. Okay. Thank you. Thank you.
Okay, thank you. So, dear participants, kindly fill the feedback form for this session, and you can rejoin the session by 11:45. Thank you.